Good morning, students. Now, today's topic is response of second order systems. So, after having gone through the response of first order system for different input signals, now the next is we have to develop uh, the response of second order system subjected to inputs like step input. So before I take up the response of second order system, I will go through the basics required for understanding response of second order system. As you are all students of electrical engineering, you have gone through the fundamentals of measurements. So in measurements you have gone through galvanometer. Galvanometer, you have studied galvanometers. In galvanometers, as you know that the galvanometer senses current in the circuit, and the galvanometers in indicating, it is an indicating instrument because it is going to have a pointer and a scale, a calibrated scale. A galvanometer, I will give this example. Galvanometer will have a calibrated scale, and then microamperes, say, and it will have a pointer. This is pointer and this is scale. It is an indicating instrument. Now I am going through the basics which is required for this topic. So in instruments, there are three types of forces that act. There are three types of forces or three types of torques. Number one, driving torque or driving force. Number two, control force or control torque. And number three, what is known as damping force or damping torque. If a force acts at a distance from the axis of rotation, it is going to be called as torque. So three types of torques act on the system: driving force or driving torque, control force or control torque, damping force or damping torque. So what is the function of driving force? So driving force is responsible for bringing the pointer from zero position. So before detecting current in the circuit, the pointer was occupying zero position. Now when current is detected, now what happens? The pointer comes out of zero position, and the force which is responsible for bringing the pointer out of zero position is what is known as driving force. So driving force is generated using many of the effects of current or voltage. You have seen permanent magnet moving coil concept, then moving iron concept, etc. So it is responsible for moving the pointer from zero position. Now, if driving force alone acts on the system, what happens? The pointer won't settle at any marking. It keeps on deflecting because it is under the driving force. Therefore, to bring the pointer to rest, to settle at some position, you have to introduce a second type of force, what is known as control force or control torque. So control force or control torque acts in a direction opposite to driving force, and it is responsible for bringing the pointer to rest position. Now, as you have all studied that in instruments you have spiral springs. So spiral spring is attached to the spindle, that is the rotating part, and it is going to undergo a twist during the rotation, and when it undergoes a twist, it generates a force, an opposing force called control force, and it opposes driving force, and it brings the pointer to some position. So that is what is known as control force. Next, if third force that is called as a damping force. So in second order system, you very frequently come across the term what is known as damping. So damping is a third type of force which is responsible for successful operation of any indicating instrument. So what is damping force? Now what happens in instruments? The moving parts will have inertia. As you all know that when a body possesses inertia, if the body is at rest, it cannot be suddenly set into motion. Or if the body having inertia is already in motion, you can't suddenly stop it. So the third type of force is responsible. What happens if the only first two forces are acting on the system? What happens? The pointer oscillate about the mean position with a reducing amplitude, and it takes time to settle. So it crosses one mark, then comes back, then again crosses. So it keeps on oscillating before coming to rest at any of these positions. So that is you have to wait for the pointer to settle. So the waiting is a waste of time. So we have to introduce a third type of force, what is known as a damping force. And this damping will act along with these two forces and it kills oscillations. So the system takes minimum time to settle at any of these positions. So that is called as damping force. You have studied what is known as in instruments. We have a kind of damping, what is known as air friction damping. So in air friction damping, there will be a piston. The piston is attached to the spindle. So when spindle rotates, the piston moves in and out of a cylinder which will have air, and air is going to be pressed. So when air is pressed in a column, so that results in a necessary damping force. So this is what is called as damping force. For example, in vehicles we have shock absorber. A shock absorber is essentially a device which generates a damping force. Okay. So you have studied air friction damping. So if all the three acts, then system takes minimum time to settle at these markings. The pointer settles. So the pointer quickly settles at any of these positions. So that is what is called as damping force. So when damping in the system becomes zero, the system oscillates. And that is the angular velocity of oscillation is what is known as omega n. Omega n is what is known as angular velocity. Angular velocity of natural frequency of oscillation. Natural frequency of oscillation. So damping becomes zero, then the system oscillates, and when the system oscillates, it will have a certain angular velocity that is called as omega n. It is expressed in radians per second. So in galvanometers, so there are three types of motion. So second order systems, study of second order system is more interesting than first order system. The reason is there are three types of motion: overdamped motion, underdamped motion, and then critical damped motion. You remember, now in overdamped motion, the system exhibits sluggish behavior. So it takes more time to settle. That is what is called as overdamped system. Overdamped system means a system having a damping which is in excess. That is called as overdamped. This is overdamped. What is underdamped? Underdamped means damping in lesser damping. With a lesser damping, the system exhibits oscillation. This is what is called as underdamping. Underdamping. That is damping in a lesser proportion. So underdamping. Overdamping means excess. Under damping means shortage. So what is damping required is not there and it is somewhat less. So that is what is called as under damped. Third one is critical damped. Critical damped means system quickly settles at the marking. Okay, that is what is called as critical damping. Critical damping. So these are the three types of motions in galvanometers. So similar to galvanometer, in second order systems also we have three types of motion: over damped motion, under damped motion, and then critical damped motion. Now we come across a constant called. Now I will explain this and then I will conclude this section. Now, what is known as damping ratio? We come across a term called damping ratio. It is known as zeta, Greek letter zeta. In standard textbooks, it is represented as zeta. So, what is damping ratio? Damping ratio means d by dc. d by dc. Ratio of damping in the system to the damping which is required for critical motion. What is known as d by dc. In over damped case, what happens? Damping is in excess. D is greater than dc. When d is greater than dc, then zeta is greater than 1. So this is zeta greater than 1 for under damped case. Next, critical damped case. For critical damped case, d by dc once again. So damping is somewhat less than damping required for critical motion. D is less than dc. What happens when d is less than dc? Zeta, numerator is less than denominator, then zeta will be less than 1. Lastly, critical damped case. In critical damped case, zeta equals d by dc. So d is exactly equal to dc. So d is exactly equal to dc. Therefore, for critical motion, zeta is equal to 1. Numerator equal to denominator, and therefore d equal to dc, therefore zeta equal to 1. So with this background, so in this class I explained what is the role of damping, what is over damped case, what is under damped case, and what is critical damped case. And in the next class I will take up response of second order system subjected to step input. So among the test signals we take step input. So step input means sudden disturbance. When sudden disturbance acts on a second order system, what is going to happen? So it is very interesting to go through three types of motion: over damped motion, under damped motion, then critical damped motion. So that is what is known as response of second order system, which I will take up in the next class. Thank you.